Thanks for everyone attending here for my presentation. My name is Ernie Bin Jiao. I'm presenting for UT Arlington, Dr. Ham's research group. Today, the topic I want to share with you is SHM for damage prediction, leveraging kinematic contact enforcement-based moving load and deep learning techniques, and also machine learning techniques. This is the content for today. Let's start from background and motivation. So initially, the bridge-based emotion, which is the tool or a system to evaluate vehicle information, such as vehicle weight or vehicle types. And later, engineer combined BWIM system with structural health monitoring and the sensing techniques to obtain structural response by using a vehicle distribution load. And actually, we can use that response to evaluate or analysis for damage, structural damage, which means the inner healthy condition. However, these days, we are not really interested whether there's damage or not in the structure. We are more focusing what types of damage and what is severity of damage. However, we all know that is really difficult because so much uncertainty and unknown factors. For example, the bridge properties and in a different environment like temperature or moisture, and also the service life will affect the response a lot. So if you wanted to develop a more accurate SHM system with BWIM signal, we have three main research gaps. The first is there is lack of study with actual moving load model. There is a lot static load model applied with different location. The concept is similar with the influence line, but actually there is really few about actual moving load simulation. The second gap is we lack of study of different severity in the actual moving load model. The third gap is because we want to know how we can do the damage prediction. We also lack of study of this one. And also we lack of study of comparison with different algorithm, machine learning algorithm for different damage. For these three gaps, I have three objectives. The first is we need to study and develop actual moving load. Also, we want to compare the static load model with actual moving load model to see what's the difference. The second, of course, we need to validate and verify that our model is correct. The first, we will use analytical solution, and second, we will use laboratory test, also field test. The third objective is we need to develop more reliable damage prediction with different machine learning algorithm. So let me first from how we can develop our actual moving load model. We use the method called kinematic contact enforcement, KCE method. As you can see, there are two different colors element. The top one, the green one, is moving element as known as vehicle, the moving vehicle. And the bottom one is bridge surface, the bridge element. So we will give certain interaction between those two contact elements. There's a lot of detail, but I need to point out the most important thing is the difference between these two contact elements. Because in the reality, this gap between these two, just imagine the vehicle on the surface. So actually that gap is mostly equal to 0, and sometimes over 0 because if there is a bump, sometimes over 0, but mostly equal to 0. But it is not how it works in simulation. We need to use one of uniqueness of KCE method to solve this problem. For that gap value, we have studied for that one. So the first is if there is no external force applied on the moving load, that value actually will keep the constant gap during the movement. And however, if there is external force applied on the moving load, the Gn will keep changing. Actually, it moves like this. Sometimes it's equal to 0, but sometimes it's lesser than 0. And we all know that is impossible in our real world. If we didn't solve that problem, we will get a simulation error, and our element will just fly out because with the wrong moving direction and wrong gap between the contact element. How KCE can solve this problem? KCE will automatically calculate and update the contact stress in the normal direction and tangent direction to satisfy this friction force equal to 0. Equal to 0 means the element can keep moving to the end as we want. And as you can see, the contact stress in the normal direction and tangent direction is directly related to the gap between elements, Gn and Gt. So therefore, by using KCE method, it can solve this problem automatically by giving the parameters. So our FE model with actual moving load can be developed. Because one of our target is compare the static load and moving load. So this is our initial static load model, and we designed 4 different severity, depends on how many percentage missing in the section view. For example, 10% missing means mild crack, and 25% missing is moderate crack, and 45% missing is severe crack. And we totally have 30 listening points, which means sensor location. And we try with 3 different load locations and 3 different crack locations. This is our initial actually moving load model. All the settings are same with static load model, but the only difference is we use KCE method to develop one-way moving load. For here, I just want to briefly show you how it works between moving load and static load, what the difference. As you can see, the force is keep adding during the movement, and the signal is keep merged together, and the signal is getting complicated. For the static load, you can see the pattern is way simpler than the moving load signal. After we develop our FE model, we need to verify our model with analytical solution or the testing. So first, I want to introduce the vehicle bridge interaction equations. So by using these 2 equations, we actually can calculate the bridge displacement and bridge acceleration under moving vehicle situation. So we can easily find these 2 values in certain time with certain vehicle location. For the laboratory test, we prepared 5 different low-cost sensors. The reason we use low-cost sensor because extra interest. We want to compare like efficiency versus price and accuracy versus price just for extra information. So we have 1 strain gauge and 3 different linear position sensor and 1 PCB accelerator. And based on the requirement of these different sensors, we need to use 3 different data acquisition systems. There are 2 purposes of laboratory test. The first is we need to make sure our sensor works well during the testing. It can be something wrong during the testing, so we need to make sure we avoid those situations. And the second is we prepared actually full-scale laboratory testing, and we need to calibrate and verify our moving FE model. And this is the other test for field test location. It's nearby UTA campus. So in the field test, we use 4 different vehicles, which means 4 different weight, and try with 3 different speed. and we make sure we are the only vehicle passing through the bridge to make sure we get the correct signal. And after we obtain the data from field test or from the actual moving node model, we need to develop a damage prediction model with machine learning algorithm. So for here, I prepared 4 different commonly used algorithms. I cannot explain too much here, like parameter settings, but I just want to point out the most important things of machine learning, the concept. In the concept for machine learning, all the data has their own weight. So machine learning is just the calculator or the system to find out which data has the highest weight related with the purpose. The purpose means it could be classification or prediction. In our case, it's damage level prediction. So we will use the actual moving node response and use this algorithm to find out which data has the best or highest correlation data weight with which one damage severity. And the other thing is we really don't want to use raw data directly because the computation time will be really low. Computation time will really bad, and the sum of insignificant information will affect accuracy a lot. So we use these 10 different equations to extract the most important features from real data. And we will use those features to use as our input for machine learning. Also, we will provide feature selection to find out which feature is most important for damage level prediction. For the laboratory result, for the short conclusion, the first is we find out one of the low-cost sensor is not good enough because low resolution. So we didn't use that for the field test later. And we find out we compared the actual testing and our FE model, and we find out that actually they have the curve fitting with the different loading and the displacement. For the field test result, I can make some simple conclusion here. If there is a highest displacement, means we use the heavier heavier vehicle. And if the time period of displacement is longer, which means the speed is lower. But the important thing is we calibrate and verified our actual FE moving node model with actual field test. For further study between analytical solution and FE modeling, we try with a lot of different parameters. For example, elastic modulus, density, and different dimension of section. Here is the displacement versus the location, bridge location. And we calculate the percentage difference between the maximum displacement, and we are glad we found a really similar pattern of it in the elastic modulus case, and also density case, also depth and width. This is the result of feature selection. So we find out the acceleration actually is really important for the damage level prediction. This is just a sample of how we can read the machine learning result, and this is the kind of most important concept here. How we can read, and we call this is confusion matrix. You can see there is the right bottom 90.3%. That is total summation of different level accuracy. And the number above the percentage, for example, the left top one, the 75 means the number of the sample. And the left bottom, the green one, 96.2% means in this algorithm, it has the ability to predict healthy condition with 96.2% accuracy. So this is like summation of the accuracy prediction result for each algorithm and the different classification. We really interested with moving node, so just look at the moving node. Overall, the XGBoost has the highest accuracy to detect and predict healthy, mild, and moderate condition. And the backpropagation, that is one of deep learning algorithm, can be find a healthy and severe condition. And this just the other more information and other testing for each testing accuracy detail. For the conclusion here is we try to develop actual moving node model with KC method, and we also try to find the better way to calibrate and verify our model, including analytical solution and actual testing. And for the result, damage prediction result, XGBoost has the highest performance to detect different levels of damage. And actually, this is like a keep going project, and we have some future work need to solve. First is we need to develop more accurate FE model. And more accurate means because for now, as you can see, I just show you one-way moving node. But actually, there are two-way or four-way. And try with larger dimensions and maybe put a different girder and rebars there to get our model close to actual bridge design. And the other is we need to collect more BWIM field test data. What I'm pointing out is field test data, because the final goal is we need to make sure our FE model result is really similar or close to real data. So we need to keep collecting the real data from the real bridge, and maybe try with the heavier truck, semi-truck. The reason we can use the heavier truck is we can get more reflection. And for now, we don't know the reflection is really important or not, but we need to try with that. And once we finish this future work, our database for machine learning can be boosted and the accuracy eventually can increase. And this project is sponsored by US DOT, and the paper is under review. Okay, so thank you for your listening.